Hey guys, welcome back. We're going to dive into phase diagrams in this one. And that's going to tell us the phases which a substance is stable, right? So under what pressure conditions and temperature conditions, all right? Let's look at the generic one here. We got a generic one. So the y-axis is pressure, right? Atmospheric pressure, and the x is the temperature, all right? We can, any scale you want. It can be Kelvin or Celsius. All right, and so let's look at this. We have area here, and all this area, like that's the solid area. That means in these pressure conditions, whatever the pressure is here, this pressure and this temperature, solids are good. They are the stable phase. In this area, right, that's where liquids are the stable phase. And then in these pressure temperature conditions, that's where gas is the stable phase. And of course, we can go from a solid to a liquid called melting. We can go from a liquid to vapor, vaporization. And we can go from solid to a gas, sublimation. Now there's these lines here. That's your melting line. That's your vaporization line. Lines are where the substance could be, right? If we have whatever this pressure is here, and whatever that temperature is there, right? That pressure and temperature, that means this substance could be a solid or a liquid. Either one works, right? Just like that water at 32 degrees Celsius. Water can be liquid, it can be solid. Not 32 degrees Celsius, 32 degrees Fahrenheit. Wow, holy cow. You can tell I live in America. At 0 degrees Celsius. Now, there's this triple point right here, right? And that's where all the lines intersect. That's where water can be, or any substance, carbon dioxide or argon, whatever the substance is, can be a solid, liquid, and or gas. Then we have this critical point. What is this critical point? Well, this critical point is where a supercritical fluid exists beyond all up in this region up here. All right. What is a supercritical fluid? All right. This is where you have, if you had a window into a big tank, and you'd see a line, right? And this would be the liquid, this would be the gas. A supercritical fluid, all right, all of a sudden just looks like a fluid. You can't tell, right? It just looks fluid. You can't tell the meniscus. You can't tell the liquid from the gas anymore. It just becomes a fluid, all right? A liquid gas fluid, right? Now, typically they're higher temperatures and or pressures, or higher pressures and or temperatures, right? And so we don't deal with that much in the lab. You're definitely not going to deal with this at home, but they exist. So that's a generic one. Well, let's look at some of my representations of two here. Carbon dioxide and sulfur. Let's look at carbon dioxide. All right. So carbon dioxide has a triple point here, 5.11 atmospheres and negative 56 degrees Celsius. A critical point of 218 atmospheres and 31 degrees Celsius. And so around 1 atmosphere here, normal conditions, which are probably in this region here, right, on Earth, carbon dioxide is a gas. And we knew that. This is where dry ice, we get dry ice down here, it's a solid, it sublimes. It doesn't ever make the liquid. You have to be over 5 atmospheres, over 5.11 atmospheres for have dry ice to become a liquid carbon dioxide to become a gas carbon dioxide. All right? And so what do I want out of these? I want you to know if I gave you a certain pressure and a certain temperature, you could tell me what phase is stable. You can tell me, you can identify where the triple point is, what this line represents, where the critical point is, what this line represents, what this line represents. That's what I want you to know from these. Nothing too great, nothing too fancy. I don't want you to memorize the numbers or anything like that. Sulfur is kind of fun because if you look at sulfur, there's right away 2 triple points. Because sulfur has 2 different solid phases. The crystal structure of the sulfur depends on the pressure and the temperature. Kind of neat. So if that's 95-ish, 95.4 degrees here, the first triple point, 1 atmosphere. Up here, most of the time, we're going to have rhombic sulfur, according to this diagram. We have to increase the temperature to get to monoclinic. All right, and then liquids over here. Okay, And so, and again, my scale is, I don't have a scale. These are not to scale. These are just generic graphs so you guys can see them. Now, if you look at these, they look somewhat similar, somewhat different in the fact that sulfur has 2 triple points. We look at water. Water is big time different. And the big time difference is the melting point line. It's got a negative, right, it's to the left, negative slope. Well, what does that mean? Well, because water hydrogen bonds, all right, when water hydrogen bonds, just like anything in hydrogen bonds, it becomes less dense. It expands when it freezes, right? Water does this, methanol will do this, ethanol will do this, things that hydrogen bond do this, right? Which means ice will float. It's kind of fun, all right? And so when we look at water, 1 atmosphere is our normal conditions. I can tell you can find out what the normal melting point is and the normal boiling point is on a graph like this. It's kind of neat, all right? Hopefully that's not too bad. Water's triple point, not very much pressure, not very much temperature. And its critical point, a lot of pressure, a lot of temperature. So those are phase diagrams. Those are just diagrams that illustrate what phase or phases of a substance are stable under what pressure and temperature conditions. All right, so hopefully that works for you guys. Let me know if you have any questions, and we'll see you next time.